impacts of the new ASHRAE standards 90.1 and 189.1, specifically on waterside design for plumbing and cooling and heating. And there's some major impacts there that we should take a look at. This is not intended to talk about everything at a time, just a few of the key points that we think might be very important going forward for engineers and customers to understand. As we work our way through this, there's a couple of things we'd like to make sure we try to hit. And basically, ASHRAE 90.1 is an old standard. It's been there for a while, so there'll be a little history of where it came from. And then as we go from 1975 to today, you'll see the comparisons of the energy usage of 90.1. And then we really want to zero in on 90.1 2010 because DOE has adopted that and stated it's going to become energy code, which is pretty daggone important. And then we want to look at what ASHRAE calls the green code, the lead green code. And that's ASHRAE 189.1, which is based on 90.1, except it's a lot more efficient. And people are beginning to adopt that as code, and we've got to take a look at it. And then we want to look at the future. Where is 90.1 going? What does 2013 look like? Then probably summarize this a little bit so you kind of get an impact on everything that's going to be happening here. So where do we begin? I think you need to understand that ASHRAE 90.1 got started back, really, the first published piece of it was 1975. For those of you guys old like me, you lived through the Carter years and the Carter energy crisis. We had gas lines. People got real concerned, and board of directors of ASHRAE said we need some kind of a standard of the energy usage in a building. And we didn't have anything at that time. So ASHRAE came up with a standard in 1975 and published it. Got revised again in 1980. It was not building code at the time. It was just a basic standard for people to look at and try to design to. So what really happened was around about 1989, the lighting people got involved, which made it a more powerful standard. So the real key thing from this I want you to understand is the first 90.1 was in 1975. Now the real change came in 1999. In 1999, ASHRAE published another code, 90.1, 1999, and DOE looked at it. Department of Energy looked at it and said, we like this. This is improving the energy efficiency of buildings, and we're going to recommend and we're going to rule that all state energy code requirements at every state must have an energy code that meets or exceeds ASHRAE 90.1 1999 by July 2004. And that was a major change. DOE is saying now that 90.1 is going to become the standard for the energy codes in all states. And that was a huge change, and this is when this thing really got to be interesting. If you look at the history of ASHRAE 90.1 over the last few years, you start taking a quick look at a timeline. Let's look at 90.1 2004 as a place to begin. Today, we're dealing with 90.1 2010. If you look at this chart, that's a 30% increase in the energy efficiency over standard 90.1 2004. And that's a huge reduction in the amount of energy a building would be expected to use. Now, look at 2013. 2013, they're aiming to get 50% improvement over 2004. 50%. And that's a huge number if you start looking at it and start dealing with it. So now we're getting to where we've really got to concentrate on specific actions that we can do to save energy in a building. And we want to pick this out a little bit and look at the water side. But before we go there, a little more history for you to understand a few things. ASHRAE has several different energy codes. The ones that we really focus on today are going to be 90.1 and 189.1. And the BOD on this chart is nothing more than the Board of Directors of ASHRAE. The ADEG is just an advanced design energy guideline for buildings. It's a very aggressive energy code, excuse me, not a code, but a design guide for designing buildings to be more efficient. Now what I want you to look at is something called net zero energy. Look at the year 2016 on the red line. That's when ASHRAE's advanced design guideline, not a standard, guideline, they're targeting zero site energy usage 2016, and I'll define it for you in just a second. Look at the green code, the so-called standard green code that USGBC was a part of, lead people are a part of, they've approved it. They're targeting 2025 roughly to be a net zero energy building. Board of directors, the black line, wanted to get there by 2031, and your blue line is standard 90.1, doesn't target getting there yet, except it's improving. And that's kind of the base all these other codes come from. Now, what you probably need to understand a little bit as you look at this is what is this net zero energy building thing all about? What does it mean? And there's two basic definitions everybody accepts. And the idea is this, that net zero site energy would be that you'd have a building site with renewable energy on it, photovoltaic panels, whatever it may be, enough to generate the power or the energy that you use, that you would generate enough renewable energy to offset the power that you use or the energy you use in that building. May not be at the same time, but over the course of the year. Net zero source energy means that, okay, my building site's not big enough to put wind turbines on. I can't do it. All right, so what they're doing here is saying very simple, you can still be a net zero energy building if you pay for this someplace else, if you purchase the energy from a renewable source. So now there's two different definitions. One's on-site, one's off-site, but both are extremely important as we move forward to what this net zero energy thing is all about. So if we look again back at ASHRAE standard 90.1, 2010, which is kind of the base for all the standards we're looking at, it's important to understand ASHRAE is dedicated to driving the energy usage in this country in buildings to net zero. Now, how quick we get there, we don't know. But the goal is to continuously push to get us to the point that we can make the claim that we're net zero energy. That's the key issue. So why are we all of a sudden concerned a little bit more about 90.1 than we have in the past? I think you see where the efficiencies are being gained. And I think this is an extremely important slide for anybody involved in the industry to understand. ASHRAE 90.1 2010 was reviewed by DOE, Department of Energy, and they determined that it saved a bunch of energy over the 2007 version, which was about 18 percentage points in this slide. But the key thing is here is DOE ruled that effective October the 18th, 2013, this year, every state must have an energy building code that meets or exceeds the efficiencies of ASHRAE 90.1 2010. That is a pretty daggum strong statement. Now, that gives the people 2 or 3 years to get there because the code was a 2010 code. Now, where are you with your state? You'll see a link on the bottom of this slide. If you go to it, you can check your specific state out to see what code you're on and where you are. Now, a lot of states will ask for an addition. They'll ask for another few years. They'll request an extension to do this, and that normally is approved. But sooner or later, all states are going to get here. There's no way around it because this has happened, and this is why we're taking the time today to talk about it a little bit. So specifically, what are some of the things that are impacting the Waterside design that might be of interest to us that are in the hydraulic side of the business? I think very fundamentally one is like this plate heat exchanger one. Very simple. In the code, 90.1, 2010, all plate heat exchangers must be ARI approved. Very simple thing, but those of us who've been in the industry knows there's been a lot of areas here for improvement and a lot of confusion over what was the capacity of a plate. Now we got a standard that says it shall be ARI approved. So simple for engineers that may be involved, make sure you're getting your specifications on all plates immediately that they're ARI certified. Very simple. Lead people pushing this, 90.1 is pushing it, and that's pretty much the new, I call it the law on plate heat exchangers. What are some other things that might be really interesting? I personally find this one really interesting. I highlighted in red, pump head. Mandatory that everybody must calculate detailed pump head loss calculations for the critical circuit for the pumps on your job. That means that you got to go through, look at each device, each pipe, each fitting, each check valve, each elbow, calculate the actual head loss, calculate it, and put it in your file. That's the way it's been interpreted. So in other words, we're saying that we have been overheating pumps. I think those within the business kind of understand that, but this is where it's headed, and this is a big change, and you got to do this by when? October 2013. So if you look ahead of this, how are we going to do this? Well, if you go online, there's a lot of free applications available to you to make this easy for you. There's a little handheld one available that allows you to calculate pipe size, head loss calculations. It's a very efficient way of doing it, and it's online for you, very, very easy to come by. Also online, there's free calculators for sizing systems and calculating total pipe head. Different languages, also supports ASHRAE 90.1. So there are tools out there to make what you've got to do much easier to handle going forward, because this is a significant change now. You've got to do these head loss calculations, and you've got to put them in your file. In fact, these calculators, you might take a look at this screenshot, actually show the number of elbows, the length of pipe, the pipe runs, and you've got everything you need right here if you go through it, and it gives you the total pump head. And you can print this off, put a job name on it, throw it in your file, and you've met the requirements of the code. Here's another little screenshot blown up a little bit further, showing the particular heat exchangers, chillers, whatever may be in it. The point is, you've got to do this detailed head loss calculations, and there are tools out there for you to make your job easier. It has become the law. You have to do this. Moving on ahead, what are some other things that might be of interest to us? We mentioned this plate heat exchanger, so what is a Waterside economizer? Why are we talking about that? Let's take a quick look. This is a fairly significant change to the code that you should become really aware of. Now, real quick, this is air or water side economizers, so you can do it either air or water, your choice. Now, the changes are in red here. I try to highlight them. 1A, 1B climate zones. The country has been broken down by DOE into climate zones. And the only exception here is where zones 1A, 1B, and you might look down below that, if your load is over 54,000 BTUs, what is it, about 4.5 tons, you have to do air or water side economizer. So the first question I would ask is, where is 1A and 1B? That is really the only exceptions to the code. Well, here's the DOE map, and everybody in this business needs to get familiar with this. To the left is the dry B area of the country, which is pretty much, western part of the country we consider dry. To the eastern part of the country, we consider more zone A. These are just proposed climate zones. And if you'll note, the only exception was 1A and 1B. The only 1A I can find is Miami, bottom of Florida down there. I haven't found the 1B yet. I don't see one on this map. I'm sure it's around somewhere, but it's not in the continental USA. So the only exemption for air or water side economizers that we are allowed in USA, continental USA, is Miami, 1A. That's it. The rest of the country has to deal with this. You can do water or air side, your choice. But that's a huge change from the old code. We now have no choice but to start looking at economizers on all jobs. So what else does the code say about the water side economizers? Now, we know air is there as an option, so you don't have to do water. You have to do air or water. But if you're going to do water side economizers, what does it say about it? And again, I think for the first time they're defining what should the capacity be in BTUs on the water side economizer. So let's look at the first piece here. It very clearly says that you've got to calculate the cooling load on your building at a 50-degree dry bulb, 45-degree wet bulb condition. So when you're running your loads on your building, you might as well go ahead and plug this in as a number and pull out your cooling load at 50-degree dry bulb, 45-degree wet bulb, because those are the BTUs you're going to have to size your water side economizer on. And that's a pretty powerful statement when you see that. Now, there are some exceptions that you can see in A, B, and C, which we don't have a lot of time to deal with today, but basically they apply to where you got computer rooms or data room type situations where you got heavy sensible loads. There are different design numbers available, also exceptions. Exception C is where you cannot meet the humidification load of the building. But normally, you have to calculate the cooling load at 50-degree dry bulb and 45-degree wet bulb and size your economizer, water side economizer, on that number. One other extremely important thing that people are blowing by, and it's really kind of sneaking up on people, is this last point: integrate. integrate the economizer control, 6.5.1.3. What does that mean? If you read it, it says, and I highlighted in red, it means you're able to run the mechanical cooling at the same time you're running the economizer. In other words, your economizer is running, and if you can't quite get cold enough water, they want you to run the mechanical cooling in series at the same time. That's a huge change, and it's going to have a major impact on your piping and how you do things. It may actually require you to have two different cooling tower cold water supply temperatures, which a lot of people haven't quite figured out yet. In other words, if you've got a chiller with a water-cooled chiller with a condenser, that centrifugal chiller, what kind of chiller it may be, may need 60, 65-degree condenser water and doesn't want water any colder than that. The problem with the Waterside economizer, you want as cold a water as you can get. You want it as cold as you can possibly get. So how do you work that out? Well, what may happen is you may wind up having to have two supply and two return water connections to your cooling towers because of this chiller head pressure control issue. In other words, it may wind up looking like this next slide. You may wind up showing two sets of pipes out to your cooling towers and two sets of pipes back, and you may wind up with a cell or a cooling tower dedicated to the Waterside economizer, because you need to the Waterside economizer coming from the cooling tower as cold as water as you can possibly get. Yet your chillers may not want that cold water, may not be able to operate that cold water, but they've got to run. Remember, we have to integrate the Waterside economizer in with the mechanical cooling and run them both at the same time. So we've got to have two different water conditions for our chillers and a Waterside economizer. You might note we added a three-way valve on this particular slide so that that dedicated cell can either service the plate heat exchanger, which is ARI, and or the condenser, one or the other. So we have the ability to swing that tower back and forth. But this is going to catch people by surprise sometimes, and it's something we need to be trying to help people understand. Now, when you go to integrate, what does this mean? And I want to caution you a little bit. I've flipped over now to the chill water side, the chill water piping. This is the cold water piping, the 12,000 BTU per ton side. I'm talking in terms of the return water, 45, 55, whatever numbers you may be looking at. And what I want you to realize is, in order to integrate the Waterside economizer in series with the mechanical cooling, I have to install the plate or the Waterside economizer on the return water, on the return chill water. So with this particular slide, let's say your return chill water is coming back at 56 degrees. Then I take the economizer and I knock the 56 down, let's say, to 53. The 53 water goes to the chillers and knocks it down to 45. So now I've got the Waterside economizer working at the same time that my chillers are working. I got them in series. I've integrated the two to meet the code. Now, why would ASHRAE put the word in there, integrate? Why is that so critical to a Waterside economizer? If you would slow down a little bit and realize this, if we integrate them, if we put them in series with the chillers, then we can turn on the Waterside economizer where at higher temperatures, where at higher wet bulbs, and we can still get some energy savings by turning them on a lot quicker. So it's very simple. We get more operating hours. We put it on a return chill water. We're able to reduce the return chill water temperatures, and we can operate higher wet bulbs. Caution you again, because a lot of people, again, need to be reminded of this. We may need two different cooling tower water temperatures coming from our cooling towers. You need coldest water possible for the economizer, but your chillers may not be able to handle that cold water, and you may have to have a separate setup for them. Another caution would be, as you download in series the Waterside economizer, as you pull BTUs off your chiller plant, the flow rate through the whole system is not going down, but you're reducing the tons or load on the chiller plant. If you get that load too low, you got to watch out for short cycle of chillers. That's an issue a little bit deeper we have time to deal with today, but we can certainly get into it if anybody wants to talk about it. Last but not least, there's a lot of discussions about elevating the supply chill water temperatures in order to save energy. That makes a lot of sense, but when you go calculating that, make sure you understand you've got to keep water cold enough to maintain the humidity requirements in your building, whatever those numbers may be. So you can elevate your supply chilled water temperature at light loads, but you got to make sure you keep it cold enough for your cooling coils to take care of the humidity problems. So basically, if I had to kind of summarize what the impact of this Waterside economizer is, this is kind of a step-by-step procedure here. The key thing is you've got to have the cooling load at 50-degree dry above 45-degree wet bulb. You got to decide whether you're going to put your economizers in series or parallel. It's going to be series because the old way of parallel you cannot integrate. You got to look at your cooling tower piping. You might need 2 sets of pipes. You may need a dedicated cell for the Waterside economizer. You also want to look at what is the required chilled water supply temperature at the lower loads. If you can raise the chilled water supply temperature and still maintain humidity conditions, you get more hours of operation. You got to calculate the approach between the cooling towers and your plates, select your heat exchangers, and come up with a control sequence. Now, we went a little deeper here than normal because I wanted you to realize we're going to hand this out. We're not going to spend a lot of time with it, but here's the same step-by-step process we just talked about on ASHRAE 9.1 2010 Waterside Economizer. Just handing you this. I want you to take a look at it a little bit later on. This is step-by-step, a little more details of the slide we just showed you. It tells you how to do this and what to look out for. Also, you can start looking at wet bulbs to help you understand why ASHRAE pushed series integration. We're talking about the hours of operations. There's a little bin chart for RDU Airport showing the hours below 50-degree wet bulb. And just as you see this, as we get more hours of operation by being in series, we get a faster payback. We save more energy is the whole issue. Here's a last little example of a typical layout of 4 chillers and 4 towers. And the message is, again, because this is the big message I want you to get. You may need 2 sets of pipes out to the towers, back to the chillers. Real fundamental statement. People are just not used to thinking that way. In this case, we have a dedicated cooling tower cell to the Waterside economizer with a 3-way valve to the chiller for you to turn it on. And we got 3 cells dedicated to the condensers on the regular chillers. In other words, we can give you cold water to the Waterside economizer, run the economizer. We can run the other chillers at a higher temperature, and we can integrate the whole plant together. And that's what you got to do to meet the code. And this is the big message we need to get everybody is slow down. Look at your piping. Look at your chillers. What condensed water temperatures do I need? What water temperatures can I make for the economizer? We have a control sequence we're going to hand to you as well. We don't have time today in a short little seminar we have here to go through every piece of this. But again, this is an actual control sequence on a project. It works great. And the amazing thing about this was we got a lot more operating hours than we thought we would because the Waterside economizer is integrated in series with the plant, and we're able to turn it on at higher wet bulbs. We're able to get partial Waterside economizer going on at a lot higher temperatures, and that is really making it pay back a lot faster. What are some other changes that we might want to look at as we start looking at it? Here's a proposed addendum to ASHRAE 90.1 2010. And I should slow down and explain this to you. The ASHRAE standards are under continuous maintenance. 90.1 is normally republished every 3 years. So normally the next one would be 90.1 2013. In between those time periods, you can go online and you can offer an addendum to that for the committee to look at and consider. This is an addendum that was proposed, and you might notice this talks in terms of taking a cooling tower and turning the flow rate down 50%. Turning the flow rate down on a cooling tower 50% to become building code. And that's in the red. This is what this is all about, and this is to make sure you're going to get dry air disease on your cooling towers. It's the same thing we've been preaching a long time. ASHRAE now has got an addendum out there to do this. As a matter of fact, I checked on this one yesterday. This addendum has been passed. This addendum has been approved, and when ASHRAE Standard 90.1 2013 comes out, it'll be a part of the new code, part of the law. But it's already been passed as an addendum. So just so you understand, that's how that works. Are the other issues there? Absolutely. Let's go back to the old concepts of hydronic variable flow and two-way valves. What are some comments here we should take a look at? Take a real quick look at this. I think you see the variable flow concept still here, but let's take a quick look. It says what? It says anything exceeding, what, 5 horsepower. We've got to start looking at variable speed. And what they want to do is be able to take the flow down to 50% of design flow at 30% energy, 30% kW. That's kind of the desire here. In other words, the two-way valve, variable volume pumping issues we dealt with in the past are still here. They're getting tighter. They want to do more and more of it. As a matter of fact, they want you to reset the differential set points out across the two-way valves, out in the building, to no more than 110% that required for full flow through the heat exchanger. That's kind of tricky, but that's what they're saying. They're saying if you got a DDC control system to take the differential pressure and reset that control point for your variable speed drives downward until a valve position on one valve is nearly wide open. Translation, they want you to run at the minimum speed possible to keep the system under control and keep it working properly. At the minimum speed possible, the maximum energy savings possible to make sure the system still works. That's the change that we've got to deal with going forward. I'm not sure how we're going to do all this, but that's the way the law is. We've got to start thinking about it and figure out how to handle it. So here again, I've just kind of taken that exception out of that code. I call it the law because a lot of people haven't picked up on this. The main point is you can no longer put in a fixed differential pressure for variable speed pump control in closed systems. You've got to reset it continuously downward to the minimum number you can get to and still maintain control. That's how you're going to get the maximum energy savings. That is a message you need to take home. That's what you need to understand. All the other comments on hydronic design that we probably should take a look at, and this is a little bit old, but it clarifies some things. Very simple, it says, in a chill water plant, and in the second paragraph now you see at a boiler plant as well, if a boiler or chiller goes offline, we have to isolate it. We have to stop the flow through it. A boiler and or a chiller that goes offline, we have to stop the flow through it. There is an exception if there's some minimum flow required to protect the equipment. That's okay. But what this means, if you've got multiple boilers and multiple chillers in a plant, those boilers and those chillers not operating, you've got to stop the flow through them by design. And that's a little bit tricky, but you got to make sure you understand that. How about on water source heat pumps or fan coil units? What's some comments there? Well, very simple. Here's a little comment on water source heat pumps. All water source heat pumps have to have what? 2-position automatic valves. Interlock to shut off the water when the compressor's off. We've been doing it that way. This is clarified. I think it's very simple. But take a look at the variable speed bit or the reduced energy bit. Last paragraph. Total pump system power exceeding 5 horsepower shall have controls, variable speed, and or devices, again, so that half flow we only use 30% of the kilowatt hours or 30% of the energy. Very clear that water source heat pumps have to have two-way valves. Very clear you can be using a lot of variable speed on. Are there other issues that we should take a look at? Absolutely, and I think this is a huge one that most people that I talk to have not picked up on yet. And this is the law, October 2013 this year. Look at pipe sizing. 90.1 2010 specifies the size pipe. What? Yeah, specifies the pipe size in a table, and here's the table. And the interesting thing about this to me was it's also based on whether it's constant flow or variable flow. It's also based on whether you are running less than 2,000 hours, 2,000 to 4,400 hours, or 4,400 hours out of the year. In other words, your pipe size is going to be related to whether you're varying the flow through it and how many hours in the year that you're running the system. And that's a huge change. Well, ASHRAE has never in the past taken this strong a position. So we got to deal with this table. So now you're sizing your pipes. How are you going to do that? How are you going to deal with this as you do your routine design? Let's go back to those online calculators we talked about. These are free online calculators that a lot of them have built in this ASHRAE table Here's an example of one. ASHRAE 90.1 max pipe size. In other words, if you put in the hours of operation, which you've got to put in, obviously, nobody else knows that. You put in variable flow. It's going to give you the max pipe size and max flow and size your pipe accordingly to meet the ASHRAE guidelines. Again, there are tools out there to make this easy for you, and you need to start thinking in terms how you are going to make sure that we hit this ASHRAE pipe sizing guideline. There are other Waterside things there that we should take a quick look at as we work our way through this. And very simple, let's look at a large chiller plant. There's a section 90.1/2010 that very clearly says that you've got to do domestic hot water heat recovery if you have a central plant over 6 million BTUs installed capacity and the service water domestic hot water load exceeds 1 million BTUs. In other words, they want you to take that condenser water heat that's going out to the cooling towers, recover some of that, and preheat the domestic water. That's the whole concept. And your guidelines here are 6 million BTUs for the plant and 1 million BTUs for the domestic hot water load. Very straightforward, very simple. Balance. We've been talking about balancing for years. So what's changed? Not a whole lot has changed except 5,000 square feet. Any building over 5,000 square feet that is a hydronic design has to be balanced, and a balancing report has to be documented and turned over to the owner. Has to have a written balance report provided to the building owner on any building over 5,000 square feet. You think maybe balancing might be important? Absolutely, because we have found properly balanced and properly commissioned systems can save a lot of energy. That's kind of where we're headed. Let's talk a little bit more about this balancing thing to make sure we understand what's involved here. The code has not really changed the words that much. It still says shall be proportionally balanced, because anybody in the balancing business knows if you can do a proportionally balance, then it leads you to the ability to either trim the impellers or put a variable speed drive on and not have excess head at the discharge of the pump. It will minimize the pump speed, minimize the KW, save you the most money. So overall, ASHRAE is making the statement that we want you to do proportioning balance. So we have to make sure we all understand that. We also want to make sure when we get through that we wind up in a way to use variable speed drives, trim the impellers. We want to minimize the throttling losses at the pumps. We want to make sure we minimize those to save as much energy as possible. All of this has to be written into your specifications. The engineer has to have a procedure. The reports has to be turned over to the owner if it's over 5,000 square feet. That's a pretty significant change. I went to the user manual, and for those of you who are involved with 90.1, I would highly recommend you go get a user's manual. That's the manual that explains in detail each section. And I went in and looked on the system balance. What does ASHRAE recommend on balance? Pretty very simple. ASHRAE is not telling you what kind of device to use. But here's the words for you to look at. ASHRAE is telling you what types of devices that they would approve, what types of devices they would recommend. And when you ask that question, what types of balance device does the standard require? It doesn't require any specific type, but it does list out the types that'll work. So you kind of got to understand what they're saying. So they're saying, okay, calibrated balancing valves are fine. That would be a manual balancing valves like the old circuit setters. They work fine. That's acceptable. Automatic system pressure power controls. Let's call them flow limiters. Some people have called them automatic balancing devices. I think the proper term is probably flow limiter. Another acceptable device. The third paragraph there talks about basically a PT plug or pressure temperature balance, and that can be done as well. The fourth red item down there is the pressure independent control valves, and yes, they're in the code. They're recommended by ASHRAE as being an acceptable way of balancing. So if I kind of summarize this for everybody involved in this business, what we're saying is calibrated balancing devices, like a manual circuit setter type of device, a flow limiter is one in the middle, or a PIC, pressure independent control valve at the bottom. Those are three different devices available to you, the engineer, or to the owner, or to the vendor, is acceptable ways that ASHRAE would let you balance the system and generate a report. That's the message I'm trying to give you. You got to have some way to do this. You got to have some device to help you do this balancing report. It's going to be required. Now, where are we headed with balance? And I really did a little digging on this one, and I think this is very interesting. ASHRAE NEB. NEB is the National Enforcement Balancing Bureau for Balancing Systems. It is certified people, the people that can handle the balance, people can generate these reports for you, the people that normally show up in the specification as an independent balance service. I think you may find this very interesting. ASHRAE and NEB have really been talking a lot about balance because they kind of come together here. And they believe going forward, we're going to have a standard for balance. It's not there yet, but there's got to be some kind of building performance standard. And that's being worked on to define what is an acceptable balancing procedure. As you see so far, ASHRAE is saying you shall balance, but we really haven't defined exactly what tolerances or standard to how to do that. ASHRAE never working on that. One very important thing they found out is recommissioning. In other words, when you do a balance up front this year and you get a job commissioned, how about next year? Does somebody go in the equipment room and change a valve? How do you know that you got the performance a year from now, 2 years from now, 5 years from now that you got to begin with? In other words, there has to be some procedure to recommission or monitor these buildings to make sure we keep getting the energy savings that we've been promised. And these are two big issues that are bringing ASHRAE and NEB together. Now, there's been some talks about ASHRAE and NEB combining. It's not happened yet, but they are definitely talking about it. The two organizations have a lot of common ground. The two presidents communicate all the time. But just keep in mind that this performance measurement thing in the future is going to be a big issue, a big piece of where we go with ASHRAE. Let's switch over a little bit, look a little bit at the plumbing side. Like I said, this was not intended to be all source on water source standard issues. It's to be key pieces, and I want to look at the plumbing side as a waterside design issue as well. So what is an ASHRAE 90.1 on the plumbing side? Basically, on the plumbing side, it says, as you quote this, temperature maintenance, automatic time switches or controls. In other words, they want you to cut the recirculation pumps for domestic hot water on and off with a timer or switch or temperature control. Again, trying to save energy. So I'm going to hit you with something here in a minute. It's kind of, you're going to have to make some decisions on your own how to handle this, but this is very clearly saying timer. Next paragraph says limit to 110 degrees going out to the fixtures with a thermostat. And the last one says that when you have a heating, like a domestic water heater running, and you turn it off, we got to get the residual heat out. So you want that pump to keep running, but only up to a max of 5 minutes. In other words, you turn the water heater off, you got a pump running through it. After 5 minutes, they want that pump to cut off to save the energy. We all recognize you got to have that thing running to make sure that we get the residual heat out. Now, the reason I put this here is very simple. This may surprise you the next slide, and I don't know what to tell you to do. It's a little confusing, but I went and found what does OSHA say about all this. And OSHA has a different story. Now, as ASHRAE 9.1 2010 is telling you to cut them on and off with a timer, temperature, telling you to cut it off when the water heater cuts off. But what is OSHA saying? OSHA is saying that we're worried about Legionella. OSHA is saying we want the water heaters at 140 degrees. OSHA is saying, look at the very bottom. Domestic hot water recirculation pumps shall run continuously. And now you see why I put the slide in here. I'm not trying to confuse you. I want you to realize the standard says one thing, OSHA is saying something else. What are you going to do? I can't tell you what to do, but at least be aware that this is in there and you're going to have to deal with it. So I wish I had a better answer for you, except it's your decision. So what is the impact of 90.1 on surface water pressure boosters? And this is a huge change that we should take a slow down for a second, take a look, because this is a big change in the way we're looking at things. And if you take a quick look at it, paragraph by paragraph, and this is important pieces, it says the sensor shall be located near the critical fixture or the remote fixture, to be blunt with you, and or logic that does the same. In other words, today, most variable speed pressure boosters ship with their sensor in the discharge piping as a package, which is fine. But if you were to put the sensor remotely, you save more energy, and ASHRAE is recognizing that and saying we got to do that, and or have a logic built into some kind of PLC brain that does the same thing. So that's a huge change, and I think we need to look at that a little bit. Secondly, it says no device. I think this is an even bigger one. No device, pressure reducing valve, play valve, shall be put on the discharge of a pump, pressure booster pump, period. You can use pressure reducing valves on individual floors to protect the fixtures, but you cannot put it on the pressure booster system. In effect, ladies and gentlemen, this kills constant speed pressure boosters. They're dead. This is going to be the law October the 18th, 2013, and I find most people not aware of it. Paragraph C, no booster pump shall operate when there's no demand. No flow shutdown shall be there. Translation, you shall have a hydrodynamic tank because water is non-compressible, and you want the pressure booster to cut off when there's no draw. Three huge things that we got to deal with, and I think maybe make a lot of sense. Why? So let's make sure you see where we're going with this. This slide is a pretty strong slide. I'm making the comment constant speed is dead. If I can't put a pressure reducing valve on the pump, how am I going to control the pressure? I've got to go variable speed. But when I go variable speed, I do not want, I repeat, I do not want an across-the-line constant speed bypass. I do not want that. Because if my variable speed drive were to fail, and I go across the line constant speed, there's no PLB there. I'm going to blow the fixtures off the wall. It's not an option anymore. So you want variable speed drives, multiple variable speed drive pumps, but no bypass and no pressure reducing valves. I'm suggesting to you it's the law. You best go change your specifications. Why? Take a quick look. This little simple example of a variable speed pressure booster, and we don't have the time to do all the details on it, but look at two key things. I can have a local pressure sensor on the discharge of the pressure booster, or I can have a remote pressure sensor at the top of the building. And what ASHRAE is saying is you've got to run those wires 1,000 feet up there to that remote sensor and or have the logic in a brain on a variable speed pressure booster that does the same thing. Why would ASHRAE take such a position? Well, with kind of making it real simple, here's a particular example. Your local sensor would be 74 pounds, your remote would be 30. The bottom line is speed reduction. By having a remote sensor, I can able to reduce the speed down 26% versus a local sensor only 10%. Now remember, we have this cube horsepower thing going for us. So 10 to 26 is a lot bigger than you think it is because it's the cube of that. The savings become the cube of that. Translation, again, is an example of constant speed versus 2 pumps variable speed with local sensors, 2 pumps variable speed remote sensors. Pretty significant savings. And this is only based on 6 cents a kilowatt hour, guys. So I suspect you probably should double this for most parts of the country. But the example is there. We try to let you know there's a huge savings by having a remote sensor and all the logic that will do the same. So everybody who hears this message, everybody on this WebEx needs to take this to every person you can find. We don't want them breaking the law. They need to change their specifications. So October the 18th, 2013, this needs to be in the guideline specifications for pressure boosters. Otherwise, they will be breaking the law. Now, we talked about 90.1. There's another standard out there that ASHRAE refers to as the green standard, 189.1. And why is it important? Why are we looking at another standard? Well, 189.1, if you look at the cover, there's a USGBC symbol on that cover. That means the U.S. Green Building Council has approved of this. They're part of this. The lead people have approved the standard. So this standard takes 90.1 and goes well beyond that in the energy savings and also looks at water consumption. Very simple, the reason it does, highlighted in red, is that buildings are responsible for 40% of the energy consumption in this country. That's a pretty big statement. So 189.1 gives us a way to start really digging into that and going well beyond 90.1, and that's why it's called the green standard. That's why it's referred to that. Now, why should we be so concerned about it? Very simple a lot of people have not picked up on what the U.S. Army Corps of Engineers did back in October the 27th, 2010. Yeah, that's what, 3 years ago, 2.5 years ago. The Army Corps of Engineers said that we're going to adopt 189.1 2009 today. And it's going to be the Army Corps of Engineers building code. And I found a lot of people hadn't picked up on it. Because this is not something coming. This is something that's already the code, it's already the law. So if you're doing any Army Corps of Engineering work, you better recognize that you need to be going per this standard, which is their building code. And you need to be aware of that. And we need to educate people to that effect. Now, what are some of the things in that really might be of interest to us as we look ahead with energy in 189.1? I think the main high-level thing you need to get is collecting energy data. 189.1 says that we have to collect the energy usage, the data for every energy source in a building, whether it's electrical, domestic water, chill water, hot water. We have to measure that. We have to record that and keep it forever. What are they doing? If you start off and you've got energy usage for a year from, you take a look and see which way it went. 5 years from now, you can see which way it's going. It's a tool for managing the energy consumption of your building. And when you start off, you're very efficient to make sure you don't lose it. So they want you to record this and have it available. Yeah, a very simple common sense statement. If you're trying to save energy, how do you know you saved it if you don't record it? If you're trying to cut energy back, how do you know if you cut it back, you can't record it? It's that simple. You've got to record it. If you look at some of the other things in 189.1, you'll find some interesting things in there, like this one. There is a limitation already in there on chill water and hot water pumps about the kW, the wattage you're allowed to use for pumps. And a lot of people are not even aware of this simple little thing. It's pretty easy to do. The major problem here would be if you didn't have the right pump head. If you just threw in just estimated a high-level pump head, you're going to wind up with too much kW, you're going to break it. So if you do a good detailed head loss calculation and a good design, hitting these numbers are not hard to do, but recognize there are limits on the wattage per GPM. I start looking at water usage a lot, and 189.1 is a part of that. For the first time that I've been able to find, and I stand corrected if somebody can find it for me, ASHRAE has taken a position on cycles of concentration on a cooling tower. Very simple. For the first time in writing I've ever been able to find, I've been looking for it, they are making a statement that 200 parts per million water or less is 5 cycles of concentration on your cooling tower. If you got really hard water above 200 parts per minute, they let you get away with 3.5 cycles per concentration. And if you got really, really hard water, you do some less. But for the first time, ASHRAE taking a position on cycles of concentration on cooling towers and how much water usage. Make it real simple. Higher your cycles of concentration, the lower the makeup water, the lower the blowdown. That leads you to having to do something kind of like this. And this is just a basic concept to show you what's involved here. You're going to have to put in some kind of a system for blowdown, some kind of a cycle control. And all we're doing here is looking at the conductivity of the water and maintaining it with some conductivity probe with a blowdown valve to maintain the cycles of concentration. So what may be different to people involved with this now is you're going to have to put in basic little systems now to be able to hit that code on the cycles of concentration. And at the same time, you're going to have to treat your water to make sure you keep it clean and in good shape. Another comment on the green guide, so forth, is that they are making you use low water usage fixtures. They're taking fixture counts way, way down. Look at your public laboratories here. Public laboratory, at flow rate of 0.5 GPM. Then they're putting the automatic cycles on there. They're already driving the numbers down on the water usage. You need to be aware of that because that may create some issues for you. But if you're going to do design for ASHRAE 189.1, you cannot use the standard plumbing code. You've got to come here and use these for your fixture counts. You have to design the water usage for your building plumbing-wise based on this chart in order to meet the 189.1 code. If you start doing that again, you're going to have some other issues. This is another one I think was pretty interesting. Look at paragraph C. Any condensate from an air conditioning unit, this could be a split system. This could be just a fan coil unit, split system. Could be a rooftop unit. I don't care what it is. If that system is over 65,000 BTUs, which is what, a little over about a 5.5 ton unit, which is not that big, even split system, you have to do what? Recover the condensate. Yeah, that's right. You've got to collect that condensate, and you've got to do something with it. That one is catching a lot of people off guard. They haven't even noticed. That's even a small system, over 5.5 tons. Collect the condensate from the cooling coil and reuse it. If you start trying to calculate that, you've got to size a condensate unit. There are also calculators out there. Here's an example of one, online free calculators that, based on your conditions on your site chart, will help you calculate the mass flow or the gallons per minute or pounds per hour of condensate that you're going to collect from your cooling system based on those conditions, so you can size it properly. The numbers are not normally huge, but you got to know how to size your pipe. You got to know how to size your condensate pump. You've got to collect it. It's a cute little tool available out there, free of charge, that will allow you to calculate that load so you know how to handle it. What are some other mandatory provisions that might be of interest to you? Renewable energy sources. Yeah, renewable energy sources are in ASHRAE 189.1. And it says, and let's just go to the second paragraph there, you have to design your mechanical systems for on-site renewable energy systems with a minimum rating of 13 BTUs per square foot. In other words, take the roof surface area of your building, total roof area. You have to have renewable energy sources designed on your job site at the rate of 13 BTUs per square foot of building surface or roof area. You don't have to install it today, so make sure you don't misunderstand, but you have to design it. You have to show it on your drawings. You have to be able to buy it today. And the idea behind this is, if you design your system today for renewable energy, you're probably going to take a bid alternate on it for an add-on, like solar systems, like a thermal domestic hot water solar system. Everybody uses a lot of those. You design them today. You may take an alternate bid. You may or may not buy them today, but if 10 years from now, 5 years from now, you want to add them, the design is already there. You know that your mechanical system has been laid out to accept it. It makes it a lot easier to use. It makes a little sense. But on all Army Corps of Engineers, this is building code today. Today, you've got to do this. So what are renewable energies? Here's some typical examples of them. I think they're already probably aware of it. I want to make sure everybody understands that geothermal water source heat pumps are considered renewable energy. So I just want to make sure you understand that would be a piece of this renewable source if we pull the energy from geothermal. The energy we're getting out of geothermal is a part of this renewable source, which makes it very attractive to projects. Energy Policy Act, where are we going? What are the tax credits? What are driving this? You should be aware of this a little bit. The feds have a law that will probably be renewed. The bottom line is 30% tax credit with no limit, up to 12/31/2016. I suspect it will be renewed. I can't tell you that, but you got to work 3 more years with it, and there's no dollar limit. You spend $100,000, you got a $30,000 tax credit. You spend $1 million, you got $300,000 tax credit from the feds for doing this. That is huge, and your owners need to be aware of that. You need to be telling people that, because that can make some projects work out that will not work any other way. Are there other incentives out there? Absolutely. This is a website everybody in the business should be aware of. This is a freebie. Everybody should be aware. You got the punchline at the bottom, but it will give you the tax credits or the rebates available in every state in the union is kept up to date. So everybody on this WebEx should get that website, should put it as a favorite on your web bar, and keep it, because you're going to need this information. The reason it's done this way, it changes by state. It's not the same everywhere with local utility rebates or local state credits. The Fed obviously is the same everywhere, but the states are different. And here's an example. This is one we just did for North Carolina in 2011, just to kind of get you familiar with it so you understand. Then you need to do it for your state or wherever your project may be, because it's going to be different. But that website, that one website, has it on there for every state in the union. And this is what you need to take a look at. North Carolina, you have all this available to you, and we won't spend all the time going through it, but there's an awful lot there that you can use to help pay for these renewable energy resources. Here's a typical little example of it, of one that I like to toss out as a very low-hanging fruit. Here's a little simple domestic hot water system. using a photovoltaic panel for the pump, and then, thermal hot water system for domestic water, a little heat exchange, a little tank. What we're trying to do here is get partial heat of the domestic hot water for a building. And a very simple thing here control-wise, which what people like this is very simple, is when the sun shines, the pump runs. The sun don't shine, the pump don't run. You got a little glycol in that system going out to the system outside, so your controls are about that simple. And it's very inexpensive, it's very easy to put in, and you can start some low-hanging fruit. Real simple, here's a first cost on that kind of a system, and you see the actual numbers just to kind of give you an idea of the numbers involved. And I think the key thing is there's your environmental impact. That little simple system, the cost I just gave you, has this environmental impact. So it gives people a place they can start with, I call it low-hanging fruit, very simple, very basic to use. First cost is very reasonable, and yet you're having a huge environmental impact, and you see the savings we've got without going through all the numbers, but I think you kind of get the concept. What is the payback? Everybody says, what's my payback? Well, here's a solar system in Greensboro, and based on the credits available, 30% tax credit from the feds, North Carolina's got a 35% one, Duke has a credit, you wind up with a payback of 4 years. That's just a straight payback taking advantage of the tax credits. So now you've got something that's pretty practical. I think most owners would probably go along with this if you've got something similar that's going on. And the payback may surprise you. It's very inexpensive up front, less than $10,000. It makes a lot of sense as a low-hanging fruit. It's a place to kind of get started. So what are the financial incentives for solar water heating? Back to that same website. If you want to look at just domestic solar water heating, there are incentives available from all over the country. And if you go on that website, they'll detail them out for you and tell you where to go and how much you can get to do this. So where is going on? What is going on with the future of solar renewable energy? And this kind of article attracted my attention. This is June 21st, USA Today. It's talking about photovoltaic. And the first quarter 2011, photovoltaic was up 66% of this country. This country has kind of gone a little bit nuts for photovoltaic. The first cost of the panels has been coming down dramatically if you haven't looked lately. And the efficiency has been going up. So the efficiency of the panels have been going up. The first cost will be coming down. So photovoltaic has really taken off in many ways, and you're going to see a lot of incentives. The reason I put this up here is solar thermal panels for domestic hot water are more efficient than photovoltaic. Photovoltaic catches a lot of attention, but solar domestic hot water panels actually are more efficient. They will capture more of the BTUs per square foot available than a photovoltaic panel. What I like is put the two together. Take your photovoltaic panels and run your pumps, and your domestic solar hot water systems are the other, and you've got yourself a nice little system. So what is the future? Where are we going? A couple of little quick comments. There are limitations on how much GPM per horsepower on a cooling tower. Very easy to meet. There's a code there just to be aware of it. Wouldn't worry about it too much. Let your cooling tower vendors worry about it, but it's there. And those numbers are going to get tighter because they're pretty easy to hit today, and I think in your future codes, they're going to start tightening those numbers up. So where is ASHRAE going, 90.1? What is the future with these standards? Here's a snapshot of 2001, 2013. What are they trying to do, 90.1, 2013? They're aiming for a 50% energy savings in 2013 or 2004. That is a huge goal. Will they hit it with 90.1 2013? I don't know, but they're pushing in that direction. But my message to you is going to get harder and harder and harder. That means more and more codes, more and more little details that we have to deal with. But we need to embrace this because it's the right thing to do. So what is the future? Net zero energy building is a trend. It's not a fad. People are going that way. ASHRAE is going to push it that way with their 90.1 and 189.1 codes. From a Waterside standpoint, water is a very efficient system to be using for 90.1, 189.1. You can do lots of things. So the efficient equipment, the opportunity for efficient equipment on Waterside for efficient systems like geothermal water source heat pumps and others is huge. So this net zero energy building thing is going to change the way we design systems. It's no longer going to be strictly first cost. You can forget that. You're going to say, no, this time it's going to change. This time it's changing. The least first cost will not rule because the codes are going to drive you to the efficiencies that you cannot hit any other way. So you're going to have to start looking at codes, rebates, incentives, and then the cost comes into play. In other words, our building industry is shifting. It started dramatically fast. It's going to accelerate now. There's a big fundamental shift going on in the way we design, construct, and maintain buildings. Energy is going to be the king. Water is going to be the king. We're going to have to deal with those issues, and that change is coming. Water systems fit well with that. We need to educate ourselves on these issues for 90.1, 89.1. Educate everybody we can find, because water systems are the most efficient systems on the face of the earth, and it's the way to go. We appreciate your time today. If there's any specific questions, be happy to try to answer them. Shoot us a note to this website, and we'll be happy to do it. Otherwise, have a great day. Thank you.